Welcome to Experience 3, Atomic Emission Spectra and the Bohr Model. This sounds interesting, huh? Okay, so previously we had talked about phases of matter, solid, liquid, gas, and that if I have particles in the solid phase and they start to gain energy, they will go to the liquid phase, and if liquid particles gain energy, they go to the gas phase. Well, from there, if you have elements in the gaseous state and you continue to add energy, electrons become excited and the atom becomes unstable. Oh boy, what on earth does this mean? But it must be something kind of important. Okay, so here's the deal. Now, once I've gotten to the gas phase, if I continue adding energy, I'm not going to have any more phase changes, but the electrons on the outside of the atom can get what we call excited. Excited just means that they're at a high energy level. And at one point in your science career, you may have drawn atoms with like a nucleus in the middle, and then there's these rings around the outside, or energy levels or shells or whatever you may have called them, and that's where the electrons are normally found. The electrons, there's a few just kind of hanging out there. So we're just saying now, let's say this is an atom that's already gas. I don't even know what this atom is. I guess it's got 1, 2, 3, 4, 5 electrons. Maybe it's some kind of gaseous boron if it had 5 protons. If I continue to add energy, the electrons become excited. And that just means that the electrons jump to a higher energy level. So maybe if this is like energy level 1, energy level 2, energy level 3, maybe I have an electron in level 2 and it jumps to level 3. They just jump out to higher energy levels. But high energy is always associated with instability. Whenever something's at a high energy level, it's not stable. And so we call this an excited electron. It's excited, it's got energy, it jumped up to a higher energy level, and then it realizes, Mom, I don't want to be here. And so we want that poor little electron to be able to go back down to his original energy level. Later on, we'll call that the ground state. Their original energy level where that electron would like to be found, its home base, is called its ground state. But in order to fall back down, that electron needs to emit all the energy that it originally absorbed. So if it absorbed a little energy to go from level 2 to level 3, then it's going to have to release that energy to go from level 3 back down to energy level 2. So when the electrons release energy, the atom can emit light. Now there's different forms of energy, heat and light. And when we talk about these electrons moving up and down the energy levels, we're going to refer to the electromagnetic spectrum, and specifically the visible light portion of the spectrum. And you might kind of remember the electromagnetic spectrum, that there's obviously the visible light that can be broken down into all the colors of the rainbow, and then there's ultraviolet that's even more energetic than violet light, and then it goes up to like X-rays and gamma rays, and then below red light you could have like infrared and radio waves, microwaves, low energy waves. And so depending on how much energy is gained and then how much energy is released, we could see different forms of light. And again, more specifically, we're going to be concerned about the visible light portion of the spectrum because that's what we can actually study in the lab. The light an element emits is composed of specific wavelengths of light. And you might kind of remember too that the different colors of visible light, or the infrared and ultraviolet and X-rays and gamma rays, they just correspond to different energy levels and different wavelengths and frequencies. So like if I think about a wave, like the wavelength is like the distance from either peak to peak or trough to trough. And then the frequency is like how many waves per unit of time. Now the longer the wavelength, the lower the frequency. Because then if I have like there's like a crazy wave, where here the wavelength is much shorter, the distance peak to peak or trough to trough. So that's a shorter wavelength, but then it's a higher frequency wave. In the same amount of time, I'm going to have more waves. This would be a higher energy wave. High energy. This would be a low energy. Low energy. All right, energy. High energy. Okay, so whenever we refer to wavelengths of light, we're kind of indirectly referring to the energy level of the wave. If it's a high frequency wave, there's lots of waves per unit of time, and then it's got a small wavelength. A lower energy wave is going to have a lower frequency because the wavelength is so large that there's just not as many waves in a particular amount of time. The atomic mass spectrum is the pattern formed when light emitted by an element is separated into the different wavelengths it contains. Different wavelengths or distances between crests of waves of light result in different colors. Okay, so here's the deal. Maybe you remember this from a former science life. If you look at white light and then you run it through a prism, white light is actually a combination of all the colors of the rainbow. So when you run the white light through a prism, you should see little rainbows, right? So it's kind of a picture of an incandescent light bulb, and they're using something called a spectroscope, which is basically kind of a prism that separates light into its individual colors. Each color of light has a characteristic wavelength that now we can kind of see as we separate that light into its different wavelengths and different energies. When the input is white light from an incandescent bulb, the output from the spectroscope or the prism is a continuous spectrum that has all wavelengths and frequencies. So we're not just talking Roy G. Biv. It's like every possible shade of red and orange. And it's a continuous rainbow that has all possible shades of all visible colors. Okay, so now let's say we had a tube filled with hydrogen. So it's a bunch of hydrogen atoms. And we hook up this tube to like an electricity source. And in one of these videos, I'll show you, we've got tubes that look just like this, and they're called emission tubes, and they get hooked up to these little power supplies, and we plug it in the wall. It's kind of like a light bulb. But the hydrogen gas will glow kind of a pinkish color. And so with my eyes, I'm going to see kind of like a pinky, I don't know, yeah, like a pinky purple color. But when you run that light through a spectrum and it separates it into its individual wavelengths or energies of light, you'll see specific patterns of colored bands. And so like with this pinky purple light from the hydrogen tube, it'll separate into kind of like a purple band, a blue band, kind of like a greenish teal and red. Well, what I'm seeing with my eyes is a mixture of all those colors. All the colors together look kind of pinky purple. But the prism will separate that into specific colored bands. And we call that the emission spectrum of an element. It's kind of like here they're saying an elemental fingerprint. Each element emits specific colors of light that correspond to specific wavelengths and specific energies of light that are being emitted by the electrons when we add energy. And by hooking them up to an electricity source, that's a source of energy. So we're energizing the electrons on the outside of the atom. They're jumping up to higher energy levels as they absorb this energy. They decide that the high energy level is not stable, and they eventually want to get back down to their ground state. But in order to do that, they have to emit all the energy that they originally gained. And when they emit this energy, we see specific patterns of colored bands. No two elements have the exact same atomic emission spectrum. Furthermore, no matter where a sample of a given element is collected, the spectrum will be the same. So the spectrum for a hydrogen is the same, whether I get it from a tank or I produce it in a chemical reaction and I collect the gas. No matter the source, hydrogen is hydrogen. And the atoms all tend to make these specific jumps up and down their energy levels, and then they release specific colors of light. And so here would be like we usually call this like the emission spectrum of hydrogen. And you can kind of see like the purple color, the blue, the teal, kind of like a reddish, like a reddish orange. And you can compare that to other elements. So like helium produces like some purples and kind of blues and violets and some more teals and yellow and another like red. And the reds could have like different shades of red, that they could be kind of red to us, but it might be like a different wavelength of red. Every element produces a different set of these patterned bands, these colored bands, which then means that it's a way of identifying an unknown element. That if I have this unknown element on the top, and I can compare that to the known emission spectrums of other elements, I could identify it, which is kind of what they're having us do in 21. SEP, Science and Engineering Practice, analyzing some data. So this is data from an emission spectrum. What is the identity of the element that produced the unknown emission spectrum? And what information does the spectrum give us about the source of the element? Well, kind of a loaded question. I mean, number one, the identity of the element, that's easy. We just match up the colored bands and see what it seems to match best with. Looks to me like this guy is pretty similar to strontium, huh? I'm going to say strontium. What is the identity of the element? Strontium. And now we could have a mixture of elements too, and that would be kind of fun. Like if I had a mixture of like helium and sodium. Well, I would be looking for like 3 yellow bands. I'd be looking for that one red band. And then you could kind of like pick them apart and see, okay, where do these bands match up with? It could totally work with a mixture of elements. And in fact, it really is a way of identifying unknowns. I find an unknown mineral and I want to know like what composes this mineral. One option would be to look at its bright line emission spectrum. Okay, second part of this question, what information does the spectrum give about the source of the element? Well, that's kind of a trick question. Nothing. Oh, bummer. I don't know where the strontium came from. Strontium is strontium, and all their atoms are the same. They have the same number of protons and electrons. I mean, they could be different isotopes of strontium, and they would have the same number of protons, and that's what would identify it as strontium. And as long as it's neutral, there would be the same number of electrons, and those electrons would tend to gain energy in the same fashion, as long as it's the same element. But it doesn't really tell us the source of the sample. Interesting. Okay, so we're going to dive deeper into this idea of electrons moving up and down the energy levels. But for now, the big takeaway is just that when the electrons gain energy from some kind of an outside source, it could be electricity, it could be heat, it could be whatever, the electrons will jump up the energy levels, but that's not stable. So when they want to go back down to their stable ground state, they have to release that energy, often in the form of different types of light waves. And those different types of light waves are characteristic of a particular element. Those pattern bands will help us identify an unknown element.